work, mainly it's called universal approximation theorems. First we start with a recap, a very short recap from previous seminar. Then we review two papers, both of them in 1809, one of them Sibenko's paper on universal approximation, the second one Hornick's paper on universal approximation. In previous seminar we talked about VC dimension. We showed that it's a way to define the capacity of a classification task. In this session we try to generalize this notion to the regression problems, for general problems. We also show an extension in classification task as well. So first let's start with Sibenko's paper. Learnability. What is the meaning of learnability? Assume that we have a set of samples, we have k samples, each of them of dimension n, and a corresponding target, each of them of dimension q. This is the whole dataset that we have. We assume an underlying mapping f from the n-dimensional space to a q-dimensional space, like f, such that this relationship holds for all of the samples. So the question is, if I give you the dataset, can you find such a mapping? Can we approximate an arbitrary mapping f by a feed-forward neural network? In other words, can we approximate are the neural networks, feed-forward neural network universal approximation? Why is it called universal? Because we are assuming that any arbitrary mapping we want to estimate. And so this is the topic that we want to talk about today. The structure of a neural network. This is a single layer feed-forward neural network, as probably many of you have seen before. We have an input layer, a linear transform, an input layer, an input x, a linear transform, a hidden layer. This means a nonlinearity of dimension n, and we have an output transform. This structure can be written in this form. You see, yi's, yj's, and theta j's are the corresponding weights for this layer. It's called hidden weights, and the corresponding weights for this layer are alpha j. So, and this sigma is the nonlinearity that I put here. So you can find the whole structure that you see here as a function g of x. Now, there are several questions. First one, can we approximate any arbitrary mapping f with this form of functions or not? The second question, if we can approximate a specific f, under what conditions these form of functions are capable of doing that? And second and third, what's so special about this specific structure? Why there should be a linear, well, it's not linear, it's affine. Why there should be an affine transform in the argument of the nonlinear function, and why it can be anything else, right? Why this specific form? So these are the three questions that I try to answer in this lecture, and so let's start with some definitions. I try to go slowly because you need to fully understand each of these definitions before we go to the theorems. So if you have any question, please ask me and I try to answer to the best of my knowledge. So first we define an n-dimensional unit cube as In is the space is the space of n-dimensional variables between 0 and 1. And we define the space of all continuous function on In as C of In. Then we define the space of all finite sign Borel measures on In as M. I assume that you all know the meaning of measure, but what is a Borel measure? A Borel space is a space which is created by using intersection, union, and camp selection. So this Borel space, so Borel measure is a measure that is defined on a Borel space. A signed measure is a measure that can take negative value and positive value. When you say positive measure, it means that it's always positive. Signed measure means that it can be as well, negative as well. And finite measure means that it is bounded, it cannot take infinity. So this M is the space of all finite sign Borel measures. Don't worry about these words, but we will use them somehow. Then we define the notion of discriminatory. We say that a function is discriminatory if, for a measure mu in this specific space, if for a measure mu this equality implies that mu itself should be 0. This is the meaning of discriminatory in Sibenko's paper. So it's a very abstract thing. I don't have any intuition about what is the meaning of this, but we will see later in some form. So, but keep remembering that discriminatory means that this equality means that mu itself should be 0. There is no single specific function sigma that this summation can be 0 for all y and theta. It cannot be possible, so the only thing that's possible is that the mu itself should be 0. This is the meaning of discriminatory. And the meaning of dense. Dense means I have two subsets, I have two spaces. One of them is a subset of another. I say S is dense in P if for any epsilon and every element in P, I can find the corresponding element in the smaller space S such that the distance between these two can be arbitrarily small. So let's say I have two space. This is important, we will use it everywhere. I have two space. I can, for every element in P, I can find an element in S such that the distance, let's call it B. This distance can be arbitrarily close, arbitrarily small. So this S cannot be like this. Probably it should be bigger and bigger such that it can cover all the space of P. This is the meaning of dense. We call such subspace a dense subspace in P. Like what, for example, the space of rational numbers is dense in the space of real numbers. For every real number, you can find the corresponding rational number, which is arbitrarily close. Right? So this is the meaning of dense. And sigmoidal, it's a very well-known definition. Sigmoidal functions are the functions that goes to infinity, but that goes to 1 as t approaches to infinity, and goes to 0 as t approaches to minus infinity. This is a definition of sigmoidal function. It can be continuous or uncontinuous. So these are some definitions that we will use later. And this is one very well-known theorem in functional analysis that in Sibenko's paper they use it as a tool. So I will not go to the detail of this theorem and proofs. And so, but this Hahn-Banach theorem says that assume again that you have two subspace V0 and V. We have two space V and V0, and V0 is a subspace of V. And we are given a linear functional L0 on the smaller space. This L0 is bounded by a function P, functional P, on all of the space, on all of this smaller space. Again, let's write this V0 and V. We have a functional L0 which is bounded on all of this smaller space. This theorem says that the functional L0 can be extended to another functional which is bounded on the whole space of V. This is somehow trivial, and it's not trivial at all. It has one page's proof, but it is trivial if you assume it, I don't know. This is wrong, but this was my understanding. It is wrong because we cannot draw it like this. For example, you have V1 and V2. Assume that this is your biggest space, and this is your smaller space. You say that in this region, I have a function P and another function L0, which is bounded by this P. You can say that, okay, I can extend this guy to the whole space such that it is still lower than this P. This is intuition if you assume that this space are the space of real numbers, but this is not. This is the space of functions. So each element in V is a function. For example, this V is a function and L0 is a functional on V. Just one question. Everybody knows what functional means? I forgot to say it here. Functional is something that takes a function as an input. For example, Fourier transform is functional, right? Okay, so this is Hahn-Banach theorem. Hahn-Banach theorem says that we have two spaces, one bigger space, one smaller. If you have a functional on the smaller space, you can extend it to the bigger space. This is the whole thing. There's one important consequence from this theorem. It says that you have a space S, which is a closed. This closed is important term. You have a closed subspace of the bigger space V, which is not dense in V. This is important. It's important statement of this concept. Then there is a linear functional f on the whole space such that it vanishes on the smaller space. This is the meaning of vanishing. It says that for every element in the smaller space, this functional is 0. Outside of this smaller space, it can be non-zero, but in this smaller space, it must be 0. This results from Hahn-Banach theorem, and we will use it in the next term. So, the first theorem that they prove is that assume this nonlinearity sigma is a continuous discriminatory function. Discriminatory was what? If you recall, discriminatory means that this equality means that the measure itself must be 0. This is the meaning of discriminatory. We assume that sigma is a continuous and discriminatory function. Then, finite sum of the form G are dense in C. What is the meaning of this? This was the space of all continuous function in IN. It means that if you pick any arbitrary continuous function here, you can somehow approximate it by a function in this form. And this was the first theorem that was proved in Sibenko's paper. In other words, it means that for any function and every epsilon you can find some g that the distance between these two can be arbitrarily small. So we want to turn to the proofs. The proofs of Sibenko's paper is straightforward, and then later we will see the proofs of the Hornick's paper, which both of them somehow prove the same thing but from two different approaches. This approach is much more straightforward. Hornick's paper is much more abstract, so we will see how we can handle or not. First, assume that S is the space of all functions of the form G. This is the space that we want to prove is dense. We claim that the closure of S is all of C. So, let's assume that the closure of S is not all of C. Then, the closure of S, say R, is a closed subspace, because this is the meaning of closure, is closed. Then, okay, now we have, now again we have two space. One is R, is closed, and the other one is C, space of a continuous function. You can apply Hahn-Banach theorem, which says what? Which is there exists a nonlinear functional which vanishes on this smaller space. This was the corollary that we just said here. You have two spaces. The smaller one is closed and is not dense. Then there is a functional on this smaller space, on the bigger space, which vanishes on the smaller space. So up to here, we can say that there is a linear functional that vanishes on R and S. Then, Green's representation theorem, I didn't include the Green's representation theorem in previous slide because this is the exact statement of the theorem. It says that every linear bounded functional can have this form, can be written as this form for a specific mu and for every edge. This is the exact statement of Green's representation. So, we saw that there exists a linear functional that vanishes on R, and we know that this linear functional has this form for every edge in C. Now we know it vanishes on R, so instead of edge you put sigma here. Sigma is in R, So this integral should be 0. So this doesn't look similar, right? Whereas this is the exact definition of discriminatory. We said that if a function is discriminatory, this equality implies mu equals 0. So we have reached here so far. This equality implies that mu itself is 0, which is contradicting our assumption, right? Therefore,
what was our assumption?
What was our assumption? Here we have assumed that representation there exists a linear functional for a specific mu, and we have assumed that it is 0 only on R. It is not 0 everywhere. If mu is 0, it is 0 everywhere. But it should be 0 only on R, not on all space of C. Is it okay or not?
Sorry, but this also means as well, I think so, or maybe you can correct me, this also means that the original statement, right, that the closure of S is not all of C, this
Yes.
is also wrong.
Yes.
And this is ultimately what they're trying to prove.
Yes, exactly.
Right.
At the end we say that, okay, this is a contradiction, and so the subspace S must be dense in C.
Right, exactly.
So this is a very straightforward proof. They use some tools. They know that this function exists, they know that this function exists, this theorem exists. So they just put them consequently and they prove the theorem very straightforward. But up to here, we haven't said anything about sigma. Up to here, we said that sigma is discriminatory. But what is discriminatory? What is the meaning of discriminatory? Here, they say any bounded measurable sigmoidal function is discriminatory. Then, if I have a sigmoidal function, I can use the previous theorem, right? Because now it is discriminatory and I can use theorem 1. So what is the proof of this lemma? Note that sigma can be written in this form, right? If lambda goes to infinity, and we have assumed that sigma is sigmoidal, this value, if it is positive, it goes to 1. Like the definition of sigmoidal function. Sorry that I go back a couple of times. Sigmoidal functions are functions that goes to 1 as t goes to infinity and goes to 0 as t goes to minus infinity. This is the exact definition of sigmoidal function, which is written here.
What if y, theta, phi are all 0?
Yes, exactly. If yx plus theta is 0, then the value of this function is sigma phi. It can be anything.
The phi can be 0 also.
It can be anything. You can have this value for any phi, so you can choose phi such that, I don't know, maybe it is 1, maybe it is 0, maybe it can be anything. It's in your hand. You don't put any constraint on sigma, right? Yeah.
So lambda is a scalar value?
Yes. Lambda is a scalar. I tried to write it in bold. I don't know whether you can see it or not, but
exactly.
these two are bold. These
No,
are
I was
not
thinking
bold.
lambda is also a function.
No, lambda is a scalar. Yes.
We have just one output here.
Yeah.
We have just one output layer, or actually one output neurons, so that's why
Yes.
lambda is a scalar here.
Yes, exactly. So here,
Yeah, he is proving everything.
Yeah, here
for scalar
Q-
output.
Q should
yes,
be 1.
Yeah.
Q is 1. I forgot to write it.
But if you can prove everything for Q1, then
Yeah.
I guess
Now
on
the
everything...
proofs are trivial. basically.
Yes,
Yeah.
exactly.
Even both the papers tell that.
Mm-mm.
So whatever. Yeah.
All universal approximation proofs are for scalar.
So, okay. Thus, the function sigma of lambda, which is defined like this, converges to the following function. Gamma of x, if this value is positive, it is 1. If value is negative, it is 0. Otherwise, it is sigma phi constant. So this function converges to this function as lambda goes to infinity. This is trivial.
What?
It's not trivial.
I didn't see.
We define a gamma function like this, it's not a function of lambda. Sigma converges to gamma as lambda goes to infinity. It's triple. So now we define the hyperplane pi, capital pi, by the values of x for which this hyperplane is equal to 0, and the hyperplane h, half a space h, when this value is positive, then we can write this integral. This integral should be 0, right? We want to prove that this is 0 because this is the definition of discriminatory. So this integral can be equal to this as lambda goes to infinity because it converges to gamma. And gamma, remember the definition of gamma? This was corresponding to the half a space h, and this was corresponding to the half space pi. So we can write this integral in such a form: the constant value that we have times measure over that half space, half plane, hyperplane, and the measure over the rest of the half space for every theta, phi, and y. This equals to 0. Now we show that if all of the half planes being 0 implies that the measure itself must be 0. Why? Because if this mu were positive, this would be trivial, right? If all of these values are positive, then the mu itself definitely must be 0. But here it is not. We have assumed that, you remember, mu is from finite sine Borel measure. It is not trivial, so we need to prove it. What we will do is that we will define a functional f like this, and h is an indicator function. I forgot to write it, I think, or oh yeah, it is here. That h is the indicator function of the interval theta. It should be theta to infinity. Therefore, this integral can be written as pi of mu over that half space and mu over that hyperplane, right? Because pi is the definition over this hyperplane and h is the definition over the half space. So this summation is 0. Why? Because we have that every linear combination of these things are 0. And this thing can be arbitrary. I can choose phi such that this is 1. Let's say this is in my hand. So this f is 0 for every closed interval from theta to infinity. Similarly, f is 0 for every open interval from theta to infinity. Then we can say that f of h is 0 for any simple function, and in any interval. Simple functions are the functions that are formed from concatenation of disjoint interval. It can be anything. So every function like this is simple. So we have shown that this is 0 for every open interval and closed interval. Therefore, it is 0 for every arbitrary interval and for every single function. Thus, we can put this summation cosine plus I sine, which is the definition of Fourier transform. Now, we know that f is 0 for every single function. We put these two, and we have this equality equal to 0, which is the Fourier transform of mu is equal to 0. Therefore, mu itself must be 0. Okay? So, now we have shown that if we have a sigmoidal function, and it is discriminatory, we have a sigmoidal function and it is discriminatory. Any questions so far?
Yeah, actually,
Yeah.
one question. Can you go to the slide you were using?
Here? Back.
This one. I was just wondering, what if sigma phi is 0? Can I?
What is sigma?
Yeah, but then the other one would be. Can you not solve this equation, like this equation, make it 0, without?
If this is 0, then this
Okay,
will be
but yeah, okay, then this
zero.
is 0. But if this is minus 1, but you can solve this equation in another way. Like you don't need.
You say, we say that this equality, okay, no, here. We say that this is true for any x, y, and phi. So I can choose phi, this is in my hand, this is not a constant.
You can choose
I
phi.
can choose anything.
Okay, but this is when you this is not something that's given to you.
No.
Okay.
This was in the definition of a sigmoid function.
Okay, because
You see, the definition was sigma of this.
uh,
These two I have added. Okay?
okay.
Yeah.
Okay. So I still feel like if you go back to the definition of the discriminant function, I feel like it's okay. Mu is discriminant if this is equal to 0.
Yes. No.
But okay, but
It is discriminatory if the integral of this guy equals 0 implies that the mu itself must be 0.
Okay, but then I can just say put delta to 0 and put y to 0 and choose a sigma.
It should. You cannot say that I put y to 0. It should be for every y and every theta.
Okay.
Yes.
I guess that's what this discriminatory trying to say is that if you take a set, an open set that can be characterized by y, t, x plus theta for all possible values of y and theta, okay, that would be an open set in the functional space, okay? So if you take any open set, then this sigma, the set of this family of functions, this mapping, cannot map this open set to a set of 0, to a 0. So that is the meaning of this. If it wants to map, if you want to have this mapping, then the measure itself should be 0. So it means that sigma is discriminatory in this form of definitions. So as an input, you should have an open set here. And that's why that he wants to prove that, okay, if this gonna work, if you add a lambda and phi somewhere to that definition, and if it's gonna be 0, then you should show that the mu itself should be 0.
Okay, so
But one
What-
question,
Yeah.
why you are limited to linear functions or affine functions? Still I'm not clear with that.
because we have used it here, you see, we said that I have this equality. This is the definition. This comes
Okay.
from the definition of discriminator. Discriminator says that this integral equals 0 should lead to mu itself is 0.
Sure.
Okay. Now I write this guy like this. Why? Because now then I define this h as an indicator function. Otherwise you cannot write this form here. Why could I write it like this? Because this is the integral of the indicator function. Indicator function h is from interval theta. It means that y x should be bigger than theta. The argument of h. If it is bigger than theta, then this is 1. This is the indicator function.
Mhm.
If this guy is bigger than theta, then I have h, half a space. If it is equal theta, I have this guy. If the argument is not an affine transform, you cannot write this guy, right?
So what you're saying is that
You need
you
to-
have a sufficient condition, but
Ye-
it's not necessary at all, right? So you have a sufficient condition.
Yes.
If you have an affine function, then you can write it there in this
Exactly.
form, and then
You
everything will
say
follow.
that if I put an affine function in the
Then
argument,
it
then
would
I
work.
can define an indicator function and use this property. But if you don't put an affine function here, then you need to find another
Another
trick
function.
here, another trick here, so that you can prove this equality.
I'm not sure still if the indicator function would not work. The thing is that here, if you use indicator function, this Borel set that you will input in the
Yes, you
indicator
can write it
function.
as a summation.
Sorry?
If it is an indicator function, you can
Yes,
write
yes,
this
yes.
summation.
But otherwise you can't.
Otherwise,
You should be able to do that. The thing is that if you don't write it in this form, then the set inside that mu wouldn't be half plane,
yes.
and it wouldn't behave this very
Yes,
nicely.
you don't have any
But
intuition about the shape.
yes, but I'm not sure mathematically it would be any limitation, I guess. So what does essentially it means? It means that you don't need to have this linear transformation from input to output. Of course, from computational perspective, there is a great need to have this linear transformation. But in general, there is no need to have that. At least I can't see any
Yes.
necessary condition for that.
Yes. I have a feeling that the argument here should be at least 1-to-1 mapping, right? Because otherwise you cannot write.
One-to-one
This is
between what and what?
Yes, for example, I can write it like this. For example, for every x, I can find a space, which is, for example, I can say that if x is bigger or less than something,
Mhm.
then I can write summation. So, I'm not sure, but
But yeah, I feel, I mean, your point might be right. I mean, you can still have an indicator function of that space.
Yes, absolutely.
But I don't know how easy or complicated it is to handle or go
Yeah,
forward.
totally
Probably
agree.
that's the reason. But
Totally
nothing
agree.
should change. I mean, it should be another parametric function.
Absolutely, absolutely, absolutely.
Yeah, but possibly it could like make the rest of the
Sure.
proof trickier. Yeah.
I'm not sure actually. So the main idea of the proof, actually they didn't need any of these things, right? So they only need the definition of discriminatory function and then the theorem 1, and then if they have the definition of discriminatory function, theorem 1, then they are done. The thing that they wanted to show here is that the sigmoidal function, there is at least one discriminatory function. So if you change your definition,
no,
Yeah.
it says that every sigmoidal function is
no, I mean the
discriminatory.
thing is
Yes.
that they don't need to have any sigmoidal function to be
Oh.
discriminatory. As long as you can have just one function that satisfies that theorem, then you can say that I will implement my neural network with that specific function, right? And then you will be happy.
But the proof is claim is for any
Yeah.
sigmoid.
Yes, yes. The proof is for any sigmoidal, but the thing is that why they can't say for any sigmoidal, because they have this proof. But other than that, they can say for any discriminatory function, we have this, and then we have just one family of discriminatory function. It may not be sigmoidal, but maybe something else, right? But I guess that even for sigmoidal function, probably you can prove that. The thing is that by definition, sigmoidal function, they don't need to be applied on affine functions. And that's very tricky because I was thinking, at least, actually we had a lot of discussion with Hadi about that. So I was thinking that the most of the power comes from this transformation from one layer to the other layer to the other layer. But almost all the proofs are saying that all the power comes from
Is it
that
just
sigma.
one layer? Yes.
No, I'm not talking about the number of layers or even the number of neurons. I'm just saying that all the powers, everything come from that sigma function. They are not coming from that affine functions
Yes.
or anything else, which is
Yeah.
counterintuitive for me at least.
Exactly, I mean, in all the papers that we've had, actually, like they spend a lot of time talking about the implications of this choice of sigma function, this specific choice, and then I mean it's a lot of exactly. I mean it's a lot of time spent talking about each more about sigmoidal functions than the neural network itself, the number
Yes.
of layers, exactly, which is also very very interesting.
But annoying at the same time.
Yeah.
So, okay, up to here, we said one theorem and one lemma. So therefore, we said that every sigmoidal function is discriminatory, and we previously said that every discriminatory function sigma will have a sum of this form, which is density I. Therefore, every sigmoidal function will have a sum of this form, which is density I. Straightforward. And, okay. And up to here, we were limited to the space of continuous functions. So we can, this is the problem, this is the regression problem, right? You have a data set, you want to estimate the function between x and t, and this t can be anything, this target. It doesn't necessarily need to be a classification task. Here, now we want to extend this result to the classification task. Before, I will say another tool theorem. Lucin's theorem, it says that it is again somehow trivial, maybe not. Let f be a real value measurable function on some domain A. Then, for every epsilon, there is a compact set K. Compact means closed and bounded. Every space that is closed and bounded means compact. For every epsilon, there is a compact set K. It is a subset of A, such that the measure over the rest of the space, A minus K, this is notation, measure over the rest of the space other than K is less than epsilon, and f in that space is continuous. So I have any arbitrary function but is measurable, f. It can be discontinuous. I can find a subset over which this f is continuous and the measure over that space is almost 1, because the measure over the rest of the space is arbitrarily small. Okay? Now,
What is A?
A is any space.
It's also compact.
A is also compact, yes. It is, maybe I forgot what, but yes. Now, approximation of decision function. Sigma, assume it is continuous and sigmoidal. Let f be a decision function for any classification task for any finite measurable partition of I. Note that it is finite and measurable, so Lucin's theorem can be applied. Then, for any epsilon, the finite sum of this form, there is a set D over I such that measure over that space is almost 1, and the distance between this summation and the real function that you want to estimate, it can be non-continuous, is arbitrarily small over that space. It is straightforward, it is clear, I think, the relationship, because now we can say that, okay, I have an arbitrary function f. By Lucin's theorem, I can say that there is a continuous function h and a set D, such that in this set, these two are equal, but here h is continuous. This is not continuous, but in this space, I can find a continuous, I don't know, extension or limitation something of this f, which these two are equal, and the measure over this space is almost 1. Now, I have a continuous function. I have a continuous approximation of the real function. Then I can apply previous theorem, right? So this was the result that this was discussed in Sirenko's paper. It's more or less straightforward. If you know these tools, if you know these specific theorems, it can be handled.
So all cases n is finite.
All cases, yes, it is always finite. Any finite summation, they don't discuss about this n, and I'll try to talk a little bit about the power of this n. And yes, here they don't put any constraint on it. It can be, I don't know, 1 to 100, anything. Now, Hornick's approach, it's a bit more abstract. Again, I will try to define some useful terms. First, we define the algebra. A family A of real functions on a set E is an algebra if A, this is a family of functions. If A is closed under addition, multiplication, and a scalar multiplication. It means that every function in this A, it is a combination of other functions in the same set with these operations. Next, we define the separation of points. A family of functions, again, A, separates points on set E if for every 2 points, x and y, which are distinct, there exists a function in this set, which gives different values, right? For example, I don't know, I have a set A, this is a set of function. Every element here is a function. I don't know, F1. And you have a set E, here X, X1, X2, X3. If these two are different, for example, I pick two different points here, then if A separates point on E, then I say that there exists an F1 which can do this. So I pick these 2 points and I find the corresponding function F1. I pick these 2 points and I find another function, I don't know, F2. If I pick any arbitrary function, any arbitrary points, all of the points here, I am somehow covering all of the points here. Okay? So this is just my intuition of this definition. So this A, if it has this property, it probably has many different form of functions here. The third definition is that A vanishes at no point of E. It means that for every x in E, there exists a function which is non-zero. Again, if I pick any arbitrary point here, I will find a new function here such that this condition is satisfied, right? So, if I have a set A, I say that it is algebra. It means that I'm including many form of functions. I don't know, here. All of the functions here satisfies the definition of algebra. If I say A also separates points, it means that I'm also including a whole other set of functions. I'm making it bigger and bigger. If I say A vanishes at no point, I'm also including a whole other set of functions. So I'm making this set A bigger and bigger. This is just an intuition, we will use it. Okay, we have previously seen the meaning of dense. Now here is the meaning of, as a more general form, this morning's paper, everything is extended. Rho-dense means that a subset S is Rho-dense in a large set T if for every epsilon and every element in T, I can find a corresponding element which is distance. This is previously it was norm, right? Here is rho, it can be any distance metric, such that the distance is less than any epsilon. It means Rho-dense, depending on the definition of your metric. And finally, we say that a subset S is uniformly dense on compacta in CR. CR, I forgot to write it. CR is the spaceable continuous function in odd dimension R. Right? A subset S of CR is said to be uniformly dense in CR on compacta if for every compact subset K, S is Rho-cadence. Remember the meaning of Rho-dense? Rho-K means what? Rho-K is the supremum of distance over that set. It's a bit abstract. If you read 1 or 2 times, then I think you have a feeling about it. So, what it says that? It says that for any compact set, previously, remember in Sibenko's paper, it was said that I is only here. But here we say that over every subset. It is much more general. For every subset, this space is Rho-cadence. Independent of K, then if it were independent of K, then I can say that it is uniformly dense on compact. Okay. Another theorem that they use as a tool is Stone-Weierstrass theorem. This theorem, at least I had a little bit intuition, which is the thing that I said. It says that let A be an algebra of real functions on compact set K. It is algebra, so it is a big family. It has many elements on it. If A separates points on K, and if A vanishes at no point of K, so I'm including these 2 definitions, I'm making this set bigger and bigger, then A is Rho-cadence in the space of real continuous function on K.
This is intuitively correct.
It is intuitively correct, but that's the all that I can say. It's one page's proof. Yeah.
So this whole K is definition of the previous metric that you defined the previous slide.
Rho-K, yes.
Okay.
The supremum of distance.
It's not for any distance metric.
No, no.
Okay.
This is. Okay. But for every K, it should be less than fx epsilon. We can find an epsilon that is less than for every K. Okay, so yeah, this is a Stone-Weierstrass theorem, and they will use it in here. Theorem 4 or negative 9. They say, this is much more general than the previous case in Sirenko. If sigma is a measurable function, define this notation as the class of functions of the form like this. Here A is that affine transformation that we had previously, but here is a generalization of the previous summation of neural networks. If you put LJ, all of the LJ is equal to 1, then you have a single layer neural network. But here they say the summation of this form, sigma pi r of sigma. Now, they say if sigma is continuous and non-constant. Previously we said that it should be continuous and discriminatory. Discriminatory is a big assumption. Then they said that, okay, if it is sigmoidal, I'm still happy. But here they say, they state a very much more general theorem. They say that as long as it is non-constant, I'm happy. If sigma is continuous and non-constant, then this summation is Rho-cadence for every compact subset. So if you assume this compact set K to be the this space, and you put Lj equal to 1, still you are more general than the Sirenko's paper. Why? Because you are non-constant.
But here it
And
should
you
be
don't need to be
continuous, right?
sigmoidal. What?
And here that should be continuous, this activation function.
Yeah, it should be continuous.
For this
Previously it was also
Sirenko?
continuous.
It should be?
Yes. I think it was. Continuous sigmoidal function.
No, no.
The function that we are estimating can be non-continuous.
No, that's okay. But it can you go back to the definition of discriminatory function? Did you?
Oh yeah, in definition of discriminatory function or in definition of sigmoidal, there is no continuous
Exactly.
thing. But in the theorem, they say that a continuous discriminatory function. Yeah.
And the new theorem, it doesn't need to be sigmoidal, right? It's
It
anyway.
doesn't need to be sigmoidal as long as it is non-constant. Yeah. It's very general. And just one point I forgot to say, and nobody asked, but I never used the continuous property. Here it's very subtle. It is in the definition of linear functional. They say that it is a theorem after this Hahn-Banach. They say that if a linear functional is bounded, then it is continuous. So yeah, it has to be. So this thing is continuous, and then I can use the property. So yeah, it's a. Yeah. So okay. Proof. For any sigma, this summation is an algebra, right? It is closed under addition, multiplication, and scalar multiplication. All of these things are included here: scalar multiplication, addition, multiplication. This space is an algebra on K. Therefore, now we have a Stone-Weierstrass theorem. If I can prove these two properties, then I can say that A is Rho-cadence. So by Stone-Weierstrass theorem, it's enough to show that this class, this space of functions, separates points on K and vanishes at no point on K. Then I'm done. Okay. So, first, separating points. assume that I want to show for every distinct x and y, there exists a function of this form such that gives me different values, right? This was the definition of separating points. For every x and y, there exists a function f such that these two values are different. For every, if x is not equal to y, then there is an a such that sigma of a is not equal to sigma of a of y. But this is true. Why? I can pick a not equal to b such that this is true, right? A and b I can choose, and this sigma is non-constant, so I can choose two different arbitrary things. Then I say I find a such that these two equality is satisfied. I will show that why this is true. If these two are true, then I can write this. Do you see it? Instead of a, I will put a of x. Instead of b, I will put a of y. Then I have this. Easy. But why this is true? Why I can find such an a? A was what? A is an affine transformation. So I want to have that a of x equal to y, a of x equal to a, so y of x plus theta equal to a. Yeah, it's easy. You have infinitely many choice. And y is a bad choice. W. Plus theta equal to b. And this is of dimension r, so you have infinitely many choice to satisfy this as well. So for every two x and y, I can pick two a and b arbitrary, and I can find, definitely I can find these affine functions a, such that these are equal to those. Therefore, this class of functions separates points on K. This was the definition. So, now I want to show that it vanishes at no point of K. This is easier, because I say that, okay, pick a b such that this non-constant function is not zero. It can't be zero either, right? So there exists a b. Then I will define the affine transformation like this. I will put y equal to 0 here. Then for every x, sigma of a of x is equal to sigma of b, which is not 0. Then this space vanishes at no point of K. It means that for every x, there exists a function, which is this, which is not equal to 0. So, I have shown that this class of function separates points on K and vanishes at no point of K. And this whole proof was independent of K. K was arbitrary. Therefore, this theorem is proved. It was said that if sigma is continuous and non-constant, then this summation is Rho-cadence. Rho-cadence means that for every compact set, okay, for every compact set, it was different here. Yeah. So I changed the definition a little bit. And the last theorem that I want to mention, they define a new metric. Assume a probability measure mu. We define rho of mu like this. This is similar to the thing that we saw in previous seminar somehow. It means what? It means that you find the minimum epsilon for which the measure of having a relatively big distance is very, very small, right? This we don't like, so you are saying that the measure of the things that I don't like should be arbitrarily small. The smallest epsilon that satisfies this condition is called rho mu. A bit abstract. And for this metric, we say that if sigma is continuous and non-constant again, then this summation is rho mu dense. Previously, we say that it is Rho-cadence. Rho-cadence means the supremum of distance is less than arbitrary epsilon. Now we say it is Rho-mu-dance in the space of measurable functions. The sketch of the proof is like this. I haven't gone through the complete proof because it's quite long. The first part is that if S is Rho-cadence for every compact subset, then it is Rho-mu-dense. And now we can say that if and there should be an if and only, I think, or I don't know.
Why
No, it is- no,
only?
it's correct, yeah,
No.
maybe. I don't know. But we
You
say
can,
that
you
if
can
it is
easily show that
Rho-cadence,
it shouldn't be only if,
Yes.
because this is the probability
Yes.
measure. So you may have infinite distance with probability 0. So it
Yes.
means that the maximum of distance will be still infinity.
so yeah, the first part of the proof says that if S is Rho-cadence, then it is Rho-mu-dense for every probability measure. Now that we know that it is Rho-cadence, then we can apply theorem 4. Easy. But the proof of this part is not easy at all. This is quite long. Okay. The Hornick's paper continues with the universal approximation on different kind of space and different measures, different metrics. They continue the proofs on the space of LP space and weighted Sokolov space. It's a complicated space. Is the space of all continuous all the functions that which together with all their partial derivatives up to order n, they are continuous altogether. They are continuous and of finite form. It's a very complicated space. I don't know what they looked at it, but anyway. The Hornick's paper continue to prove these things, so which is why I skipped it. At the beginning, I planned to present this paper as in a whole function, but now I try to explain the Seabank perspective. Okay, so up to here we have shown that universal approximation by universal approximation proof we can use neural network to approximate any arbitrary function, continuous or discrete. For discrete decision functions, we have shown only one proof, but here there is one important point. If we have any lack of success can rise from inadequate learning, probably we have said that there exists a function of this form, but we don't say how you can find this form. You will use some algorithm to find it. If you don't get a good result, probably it's from your inadequate learning or insufficient number of hidden nodes. They haven't talked at all about the number of terms in this summation. If you have one factor here, this n can be anything, but definitely it can't be anything because I have a feeling that it should be arbitrarily large. As large as it's better, but
Because all of one's proof is large.
yes. So okay, if your work doesn't perform well, it is coming from inadequate learning or insufficient number of nodes or lack. This is a tricky point. Lack of a deterministic relationship between input and target. This was my own question, but is that in the first slide, if you recall, we assume that there is an underlying mapping F, and we have assumed that this is constant, this is deterministic. But why? Right? There is no. I don't know why they should be deterministic. If we assume a stochastic function, does it help or not? It's not clear to me.
Probably it complicates the proof,
Yes,
makes it
of
intractable
course.
completely.
There can be multiple functions that which you can have even simple linear functions that which can be multiple linear functions having the same x and y.
Right, yeah. Yeah, exactly.
So yeah, these are the points that maybe you're starting point for the future. And the final question is that how many? Yeah, you already said that. How many terms in this summation are required to get an approximation performance.
One question, why deep networks?
Yeah, I have not included the proof here, but all of these proofs can be simply extended to the multi-layer networks.
I agree.
Yes, I have.
But again, why deep?
Yes.
No, I'm just asking why deep? Why not going for these kind of networks?
Yeah, both of them are dense and.
Both of them are dense. Just I guess that there are some papers showing that if you go for deep networks, then you can reduce exponentially n. So the n that you require for shallow networks is exponential.
Yes.
Actually, exponentially, I guess, larger than the number of neurons that you need if you go to some layers.
There are proofs that where n has to be infinity. It's not, rate of the increase is not clear.
Yeah, because otherwise, like, there is no other reason why, like, one layer, I mean, neural network with one hidden layer should not be enough, right? Because if this is,
Actually,
yeah.
Ali Reza did a lot of experiment by himself that one layer with
Yeah, but
a lot of layers do quite good.
No, of course, yeah. I mean, there should be a reason for that, yeah. Because I mean, from if we think about it like theoretically, then this should be enough, right?
Yes.
Yeah.
Even n equal to 1 is enough.
Exactly.
Okay.
Yeah. Yeah, but even the stranger thing is that they never try to connect like n and epsilon, so this kind of approximation error, so to speak.
Well, actually, I haven't gone through the literature.
There is one fundamental difference, I think, that we missed. Everything is for here for the given set x
Yes.
and given t. But machine learning does not work like that, right? It's training and testing, both are separate.
But you don't say testing set, so.
No, but in function which you generate in training, that's not universal for the testing. You never know that one. So how it behaves, who knows? You have no idea about that.
Okay,
No, but
right.
for
So,
this same thing to be applicable to the test set, then you must assume that the test function follows the same subspace
Yes.
as the. Otherwise, you can never claim anything. For
Yeah.
even one layer, even with multiple layers, I don't think you can claim anything unless you have some hunch about it.
Right. Or maybe you're like you're restricted maybe to the same set, actually.
Yes.
Yeah.
I think if you restrict it, probably even with one layer, you could do wonders. But in many cases,
Right,
you
yeah.
cannot assume that the test set is. I mean, it's harder to
Yeah,
classify
exactly.
because
Because-
such nice looking cases. I don't know.
Right. Yeah. Exactly. Yeah. Because I mean, like, especially if you're thinking about like neural
Because this
networks.
whole setup probably seems to hinge on the subspace characterization, which might not work in
Right.
practical data.
Right. Yeah. Exactly. Because I mean, you have no. I mean,
There's no
exactly.
reason.
Yeah, you have no idea.
Yeah,
Exactly.
There's no reason it should follow.
The question is that, okay, how far, and I never have seen any paper that where it is written, okay, let's say that you do all this proof using this data set, and you test using the test data set, how far the test data set should be such that, okay, I will get up to this much of performance.
But you don't
Right,
see
yeah.
the testing data.
No, let's
What you
say,
don't see, you can't say anything.
no, let's say that test data is not the same training, not equal to training data. But test data is from the training data this much distance. That we can define, right?
Yes.
Yeah. Right. I mean.
But
yeah.
let's say training data plus noise equal to test data.
Right, or with according to some distance actually.
Yeah.
So we could say like it's some
We
distance
can have
away.
several models, right?
Yeah.
I never have
Right.
seen any
Yeah.
paper that where this is at least told that for this test data, I will get this much of performance. When my performance will be deviate by this much of amount.
Right, yeah.
But one question, isn't it the definition of pack? By the definition it says that if your distance, the probability of having, let's say, classification problem, so if the number of misclassification or the probability of having misclassification is bounded on something on your data set, then this probability would be bounded for the test data actually. So this is the definition of pack. So if you can perform very well on your data set, then you can perform very well on the test data, given that the test data and the training data, they are coming from the same distribution.
Same distribution.
Yeah,
So this is
Then-
something that you should assume. Otherwise,
Yes, but that's, yeah.
otherwise we cannot.
But then, like
claim
the
anything.
question, like whether
But
this holds in
that's
practice.
not the functional way of proving the stuff.
Not
Not this
yes.
way to find out. This
No, here everything is just about the feasibility. So they are just saying that it's dense, meaning that there is a function. For any specific function in C, instead of continuous function, there is a function with the structure of neural network. And they are not saying how to find that function. And actually there is another very nice paper, very famous one, published more or less in the same year, 1890, that says that training a neural network with 3 neurons is NP-complete problem. So just saying that it just doesn't matter what these people are trying to say. There is a function, but the complexity of finding that function is NP-complete. So no hope for finding that, despite all the
Can you
progresses and
send that
everything.
paper to me?
Yeah, absolutely.
Yeah.
It's an interesting thing.
So, yeah, thank you for listening.